Okay, we're going to take a look now at the difference of means test. I've done this really with proportion, which is a mean, a sample mean. Did it quickly, probably didn't get into it deeply because I was developing the logic of frequentist statistical inference, and we're going to actually do some now. As promised, so get all this down. These data are real. A sample of 983 likely voters from 1998. So they're real and they're historic. No, excuse me, from 1996. So that's a presidential election that pitted incumbent Bill Clinton against Republican challenger Bob Dole. Clinton won. These data come from a survey. There's a boat on the water. These data come from a survey that was done in-house at the University of Mississippi. We once upon a time had something called the Social Science Research Laboratory, and it was real. It had a survey arm, and the telephone calls were emanated from here. Nationwide sample, it was a complex sample. We're going to assume it's simple random. A simple random sample, we know about that already. We could incorporate the design of the sample and all of its complexities into the statistical analysis and inference. That's too advanced for this introductory course. I do want you to know that it can be done, that this is a probability sample, or it was a probability sample in its day. It's again a complex design, and in R is especially powerful in handling complex survey designs from, and this is the key that you need to know, a probability sample. Once more, a sample where all of the units in the population have a known probability of making it into the sample. So that's what we're going to pretend we have and do a little inference. There are 533 women oversampled, not on purpose, an oversample of women, 450 men. Didn't bother us much then, but we can come through and weight things if you want. I'm going to use the gender example here for a test. And we're going to first explain that we have two variables. You are actually going to play with this data set and do things with it from 1998 using R. And here's your introduction to it. X1 here is party identification. This is an ordinal variable, and we're going to do tests of mean differences relative to this ordinal variable in two conditions, gender. But first, just thinking about a general proposition, a null hypothesis about the mean of party ID. Let me tell you how it's scored. So this goes back to data, describing data, and you need to know this. And if you're putting this into a report of your own, you would have to report all of this. The range of this variable has seven categories. So we go from -3 to +3. And again, the categories are ordered this way. -3 is strong Democrat. -2 is less strong Democrat. -1 is leaning Democrat. 0 is independent. And then the categories in the positive range of the variable mirror those in the negative range, except they're distinguishing Republicanness. Leaning Republican, not so strong Republican, and then 3, +3 in the variable equals strong Republican. And I got the mean, standard deviation of the variable. The mean is very, very near independence. It's minus 0.004. 0 itself would be independence. Standard deviation is 2.19. We're going to have another variable to deal with momentarily. Gender scored 0 equal male, and 1 equal female. And we're going to introduce a new statistic. So we've used the Z statistic, which helps us, not helps us, actually. Z's are distributed normally. We're going to talk about now a different statistic and distribution, but barely. This is really important. The student's T test we're going to do and the student's t distribution becomes the normal curve if n is sufficiently high. How high? This is plenty high. So we would treat this as a z-score in a normal distribution, as we've seen, and be just fine. You get the same answers as you would just treating it as student's t. I introduced student's t here for a couple of reasons. One is that you would use the t distribution when you have a small sample. So just write that down. T is for a small sample. T is approximately normal as n goes up, sample size. But it gets the tails of the distributions, normal versus t, are different as the sample gets smaller, and you really notice the difference right underneath 100. And it can be a profound difference if you're dealing with 20 observations or something like that. And interesting to me, because I'm a nerd, an interesting little historical aside. The student's t distribution, I taught this for I don't know how many years, assuming that the name student's t, referred to sort of behavior of data really at the ratio level across fairly small groups. And it got the name, I thought, because classes tend to have test scores that gather around a central tendency in a distribution that is described by t. That's what I thought. That's wrong. The fellow who invented or discovered the student's t distribution published his work in the very, very early 1900s. Take a look at this on Google, student's t. It's a pretty interesting story. The guy worked for a beer, a brewery. He worked for a brewery, and he didn't want his name attached to the work that he was doing in public, so he submitted the paper for publication in a prominent journal edited by a prominent statistician, and it was published, and he listed his name as student, so it became student's t. It looks just like the normal curve in large sample, and just like z, we can use it to find area underneath the curve corresponding to the magical 95% confidence interval, and we can derive from it p-values just as we did with z, and that's what I want to do here. First, we're going to test a hypothesis, so we'll have an HOs, that the sample mean here is sample mean of party identification is equal to 0. So we want to know if we've drawn a sample that is partisan in a statistically significant way. I'm using that freely now, as a frequentist would. Is the observed sample mean statistically different from 0? So if it is, then we have a partisan sample, and if it isn't, we don't. Let's actually do the math here really quickly. The mean of, and I want you to do it, you're going to have to do it. The mean of x is very, very low, very near 0, minus 0.004, minus 0, just that term just leaves us, and we're looking at this ratio, the ratio of x bar to its standard deviation divided by the square root of the sample size. All those numbers are here on the board. The standard deviation of x is 2.19, the sample size 983. Everything you need to do the arithmetic is on the board to find t, and t in this case is going to be really small. It's going to be minus 0.0582. Minus 0.0582, and the standard error term, that this should be familiar, that the standard deviation divided by the square root of n, the standard error term is equal to 0.0699. There's a p-value associated with every t-score in the same sense that there's a p-value associated with every z-score, as we've already seen. the p-value here is about 0.47. About 0.47. Now remember, the frequentist, according to R.A. Fisher, the frequentist should be looking for a 1 in 20 chance of randomly, sort of by sample error, finding an extreme value. So we're looking for 0.05 here to say that there's a statistically meaningful or significant difference between the observed sample mean and the hypothetical, what we're calling hypothetical population means, just to plug in anything there that you want to make a test against. Is it different from 0 statistically? And the answer is hell no, it's not different from 0. This is nowhere near 0.05, so we would never make such a claim here. We don't have a partisan sample according to the frequentist tradition. And we're going to do one more thing with this same formula. This formula is more complicated when you have something more complicated than a simple random sample, but I don't care that you know that until you take an advanced course. I also don't care that you know we're about to look at the means between groups, and we might want to consider that the standard deviations are different between the groups, and the formula then becomes more complicated. Some people in intro teach this. I don't. I'm going to use the same formula to test the difference between the mean, the sample mean that we get from women relative to that we get from men. So let's define 2 x bar men minus, let's do it the other way, let's do 2 x bar women minus x bar men. And those data aren't on the board, but I'll tell you what they are for men. So x bar have them hanging right in front of me. So blind I can't see. For men it's 0.118, and for women it's minus 0.107. So in both cases, not very far away from 0. So not an extremely partisan group of women, not an extremely partisan, this is just descriptively, not an extremely partisan group of men, but recall that the negative numbers are associated with Democratic identifiers, -3 strong, -2 so-so, -1 leaning, and that the positive numbers are associated with Republican categories. So we do have a partisan difference here between men and women. The average male in the sample is very slightly a Democrat. The average female in the sample, the average male in the sample is very slightly a Republican, and the average female in the sample is very slightly a Democrat. This is 1996. So if we did these data, I'm going to suggest I might look at these in class in a more contemporary survey and show you that since 1996, party identification itself can show a bigger gender gap, but we even had one then. Women were very important to the winning coalitions that Bill Clinton put together in 1992 and 1996, and at least in part that attached to a slight partisan identifier difference between men and women even at that time. It's bigger now. So I'm going to test whether this difference is one that we get by sampling chance, or whether it's one that the frequentists would say is statistically a significant difference that we would expect to see in subsequent samples from those days in history anyway. So you can plug those in here. So women minus 0.107, and so we're going to get the difference here is going to be 0.225. Right? If you put one in front of the others, if you put men over here and women over there, it's a minus and minus, which is plus. So the difference is 0.225, and we're going to use the same values same values here as we did last time. What you're going to discover, and pause to let you work it all out, is the t here is equal to 1.60 or thereabouts, and that the p-value associated with this score is 0.110. It's not 0.05. It's not 0.05. So we have an observed partisan difference in this sample between men and women. Men leaning toward the Republicans slightly, and women slightly leaning toward the Democrats in terms of party identification. But it doesn't pass that Fisherian threshold of 0.05 to say that we have statistical significance. There are a couple of things I want to say about this that are really important for you to understand and for you to be able to pair it back to me on an exam. 0.110 is t is just like z. It is proportional to the square root of the sample size. So I double the number of people I increase by the square root of the new sample size. This part of the calculation, and what that's going to do is going to make t larger. So t itself is proportional to the square root of the sample size. So think about what that would mean down here. There is a point, and it's not very far away. There is a point where we find what Fisherian frequentists would call a statistically significant result, because as t gets larger, the p-value is going to get lower and lower and lower. We're not far away here from the magic number that I want you to remember about t. When t gets to be about 2.0, in this case it's 1.60, when t gets to be about 2.0, that's when ordinarily you see p-values going underneath 0.05, and when then frequentist statisticians would say you have a statistically significant result. So this is almost significant, and this is called a two-tailed test. So we're eliminating 2.5% out here and 2.5% out here, and that's where the 5% or 0.05 magic number comes from. But there is such thing as a one-tailed test, and I'm a big advocate of it. I'm a big advocate of it because most hypotheses are not two-tailed. This one would not be. When I ask you about a gender gap in party politics, having seen no statistics at all, almost all of you would be able to tell me that women are more Democratic than men. Men lean more toward the Republican Party than do women, and the reverse is true. So we talk about a gender gap, it's already got its direction. So there's no need to eliminate both of these. Just focus on one of them. A one-tailed test for the t statistic gives you a p-value that's exactly 1/2 of what you see reported. So in R, if you've asked for a two-tailed test and it gives you 0.110, you automatically should know that the one-tailed test would give you the 0.055. So twice 0.055 gives you 0.110. The higher one's the two-tailed test, the other one's the one-tailed test. The one-tailed test is the one that you want to use when your hypothesis is directional. So you don't just want to describe the difference, whether or not, you don't want to just understand whether the difference is different from zero. You want to understand whether the difference is different from zero in a predictably directional way. In this case, you'd want to probably hypothesize that men are more Democrat, more Republican than women, and vice versa, and sort of go with the one-tailed test. The one-tailed test here is almost significant by the standards of Fisher and frequentist statisticians who follow this rule too rigidly. Almost statistically significant. And it would be if we had a couple of hundred, not even that many, just about 100 more data points, we're going to see something that people will conclude is a significant difference. In class, I'm going to try to animate this result a little bit more with more contemporary data to give you a flavor maybe for sort of how analysts might be able to quantitatively examine a really, really important issue, the gender gap in partisan identification and also in partisan voting. And we'll see with more contemporary data that this echo that might have been tossed out as statistically insignificant just given the data set with 983 observations, this echo from history is a harbinger maybe of things to come. That's it for difference of means tests and the students' t-distribution, the t-test, and the associated p-values. We'll look at p-values in more detail as we introduce more statistics. This one's over.